Hi, I'm Roland Minton. These are some of my favorite math stories. In this episode, mathematics is mind swapping. We'll look at a puzzle and a mathematical theorem described in the enjoyable book, The Simpsons and Their Mathematical Secrets. In this book, we get several examples of how the writers of The Simpsons and Futurama, many of whom have graduate degrees in mathematics, embedded little mathematical tidbits in their shows. The episode of Futurama, titled The Prisoner of Benda, is special in that the entire plot is built around a difficult mathematics problem. In The Prisoner of Benda, people use a mind-swapping machine to find out what it's like to be in a different body, younger, older, etc. After having some fun with a new identity, they want to go back to their old bodies, at which point they discover a bug in the mind swapper. It will only work on a pair of bodies once. Can they get back to their original bodies? To keep it simple, suppose in a large group of people, A and B swap bodies. The machine will not switch them back directly. Is there a way to return them to the right bodies? Pause the video and try this for yourself. Writer Ken Keeler, a Harvard PhD in applied mathematics, came up with the following solution. You need two extra people, call them C and D, to return A and B to their bodies. So we're starting here. A and B have mind and body swapped. C and D are in their right place. So let's use the mind swapper on bodies A and C, and also on bodies B and D. So bodies A and C swap minds. Mind B goes from A to body C. Mind C goes from body C to body A. We're also swapping B and D. So mind A goes to body D. Mind D goes to body B. Well, body C now has mind B, and that can be returned to its proper body by swapping B and C. So mind B goes to body B. We're good. Mind D goes to body C. Now let's swap bodies A and D. That returns mind A back from body D to body A. Mind C is now swapped to body B. Well, A and B are now restored. C and D are left reversed, but the machine has not been used on them yet, so we can swap C and D and all is well. Or if others are tangled up, we can continue to use C and D to untangle the mess. But would two extra people be enough to undo a tangle of, say, 8 people? Keeler was able to prove that it is, in what is now known as Keeler's theorem or the Futurama theorem. In the episode of Futurama that aired, the theorem is proved by the universe's top mathematicians, the basketball players on the Globetrotters. Keeler, by the way, never published his theorem in the traditional sense, but how cool is it to present your theorem and proof in a popular TV show? Keeler's theorem is not the only mathematical theorem discussed in the book, The Simpsons and Their Mathematical Secrets. Do you remember the scene near the end of The Wizard of Oz where the Scarecrow gets a brain? He then shows off his intelligence by spouting the Pythagorean theorem, except that he doesn't. What he says is, the sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side. Can you spot all of the errors in this statement? Well, Pythagorean theorem has squares, not square roots. It also applies to a right triangle, not isosceles, and starts with the hypotenuse and goes to the remaining sides instead of any two sides going to the remaining side. Other than that, okay, so what happened here? Did the actor get it wrong and nobody noticed? Did the writers get it wrong and nobody noticed? Was it satire of the true value of the wizard's diploma? An early script gives some evidence that satire was intended, but we don't know for sure. However, until reading the Simpsons book, I didn't know he got it wrong. Though to be fair, most of my viewings of the movie came before I ever heard of Pythagoras. Well, what does this have to do with The Simpsons? The writers of the episode Springfield or How I Learned to Stop Worrying and Love Legalized Gambling had Homer confidently say this exact line after putting on Henry Kissinger's glasses. And no, I don't think I'll explain that one. This had the wonderful effect of people exploring whether the so-called Scarecrow theorem is true. For an isosceles triangle as shown, isosceles meaning two sides the same length, is the square root of b the same as the square root of a plus the square root of a? See if you can decide. Well, it's not hard to find a counterexample. In mathematics, a statement like the Pythagorean theorem is only considered true if it is always guaranteed true. One example where a statement is not true, a counterexample, makes the overall result false. If you don't want to mess with triangle lengths, this argument should convince you that the scarecrow is not always true. Suppose it were true for the lengths A and B shown in the picture. We'll make a new triangle with the same base B, but very large h extended up, and that will enlarge the value for a. With a different, you get a different square root of a plus square root of a. That can't equal to the same square root of b again. So the scarecrow result is not true. 3 math majors at Augusta State University had an inspired bit of mind inversion and asked this question: is the scarecrow ever true? Not just false because it sometimes doesn't work, but comprehensively false because it never works. Well, let's try this one, and we'll avoid going down a geometrical rabbit hole. What can we say about the value of a compared to b? Well, if a was less than b over 2, the sides would fold down without touching, and therefore we wouldn't have a triangle. But starting with square root of b equals square root of a plus square root of a, we get square root of b equals 2 square root of a. Square both sides, you've got b equals 4a, and that leads to a equals b over 4. But b over 4 is less than b over 2. This value of a does not produce a triangle. The scarecrow is never true. Well, mathematics has a wonderful, though sometimes maddening way of forcing us to think in different ways to explore the world. We don't literally swap minds with colleagues, but somebody having a different way of looking at a problem can get us to see the problem from their perspective, often creating a breakthrough in solving the problem. No need or desire to try to go back to our old minds.